All right, now we're going to talk about, as the first lecture, recorded lecture in 477, 677, we're going to talk about abstract data types and their implementation. We'll start with stack. Now, ADT stands for abstract data type because we have the abstract concept of a stack, and then later we talk about implementation. Now, in a stack, there are four operators, classic operators. You start with an empty stack by initialize, in other words, creates a new empty stack. Empty is a Boolean function which returns true if the parameter is empty. Push inserts a new item into a stack, and pop deletes an item and returns the value of that item. And these rules hold regardless of how the stack is implemented. Here is the easiest way to implement stacks using the so-called array implementation, where the items of the stack are stored in an array. The array is allowed to have fixed length, but we only use the first part of it. So the number 3 here indicates that the stack consists of only those 3 items. And this is an illustration of the stack in the usual way, with the bottom, next, and this is the top element of the stack. Now, the way you pop an item is you return this top item and decrement the size. The way that you insert an item, suppose for example we want to push S T, where S is the name of the stack. So what is S implemented as? S is implemented as an array A and an integer size. So we're going to push, you could think of this as a structured type. We're going to push the item T onto the stack, which means that we increment the size, and we put T here in the position of that. Now the W, it could be there because the stack was once that size, but that doesn't matter because we're never going to read it. We don't have to delete things when we pop. We simply are never going to read them again. How do we insert? I already told you that. How do we test that it's empty? Well, we look at the size variable, or the size field. If that's 0, then the stack is empty. You initialize a stack. For example, if I said init s, the way that would be executed is only with one thing, and that is to check the size to be 0. I wouldn't have to delete anything at all. This is a linked list implementation of stack. We have a linked list here where each node has 2 fields, the item field and a pointer, which points to a node. And for example, in this stack, the bottom element is B, the top element is V, and we have a variable, a pointer variable, which points to the top element. We don't have a variable that tells you how many things are in the stack, but the function empty will return true if this particular pointer is null, such as here. Now the bottom of the stack has to have a null pointer so that when you get there you know you're done. Now the way you add something in this situation, or the way you implement push, let's say we're going to push a new variable T here. Then we go here, we do a new variable here, we point that here, and then we redefine the pointer S. So this is an insert here. All right, let me back up and show you how to do a delete. Well, in the delete, what you simply do is change the pointer variable to point to what the top element points to. Now this is the new top element, and you notice that this item is unreachable. We no longer have a pointer to it at all. So this brings up the issue of garbage collection. This particular node in memory takes up space, but it's not being used for anything. That makes it garbage. And you can do your own garbage collection, or the system will do it for you. But the simple solution is not to worry about it. If your program is very short, once it's finished running, then all the memory will be cleared anyway. All right. Then the next abstract data type is a queue. And a queue is similar to a stack. We insert items and we delete items. The only difference is that when we delete an item from a queue, the one that's deleted is always the one that was first inserted. In other words, the oldest item in there. Otherwise, we have the same operators. We initialize empty queue, we check if it's empty, and end queue, which is like push, put the new item in. But we can think of the line of people at a theater getting tickets. That line is a queue. People are inserted at the rear of the queue. When somebody arrives to buy a ticket, they get to the end of the line, while the front of the line is where people are deleted. The way to get deleted from the queue is to buy a ticket and leave. All right. The simplest way to implement a queue is as an array. It's actually more complicated than an array implementation of a stack. But we have items in an array, and then we have variables representing the positions in the index, the indices of the positions of the beginning and end of the queue. So the actual queue contains only these letters. Z is the front item, and T is the rear item. Now, as we insert an item into the queue, we have to expand rear and increment this number. If we dequeue an item, we have to decrease the value here, which means we increment the value of front. We would change that to 3, thus indicating that Z has been deleted. Now you can see right away what the problem is. The problem is that we could run to the end of the array even if we have items in the queue. We could have this moved over. Suppose that rear is 7, front is 2, and we want to insert someone. Well, there is an empty space, but we can't use it because we're already at the end of the queue. Here's an example of false overflow. Suppose that the queue is not full, meaning it doesn't use the whole array. However, the rear item is already to one end of the array, and we need to insert one more item. Where are we going to put it? We've run out of room. Now, there are 3 solutions to the false overthrow problem for the array implementation of queue. One of the solutions is what I call slide. When the queue is full at one end, then what you can do is copy the items over at the front end of the array, leaving space here. That we'll call slide. Now, another one is called wrap, and that uses a circular implementation, so that when we get to the end, we can have a queue that wraps around and starts incorporating. For example, if this is the item F, T, R, then that means that the front item is F, the rear item is R, and it theoretically wraps around that way. Now that has its problems. Both of those implementations have their problems. The problem with slide is that it costs a lot of time to slide everything over. And if you're in a real-time situation, such as implementation inside an operating system, the slide might take enough time to cause some kind of trouble. Now, if the queue is nearly full, you'll have to slide frequently, and that's called thrashing, and that could really slow things down. Now what about wrap? Wrap has problems too, because what happens when this front, no, this is rear, when you keep adding things and it collides with the front, then it's completely full and you can't tell whether the queue is empty or full. All right, now large array is the dumbest solution. What that is when you write your program, you allocate enough space in the array so that false overflow never happens. So the false overflow never happens. Now, how big does your array have to be? Well, you have to know in advance an upper bound on how many items will be inserted into the queue. For example, if you're running a program where you know that during the entire lifetime of your program, a total of no more than 1,000 items will be inserted into your queue. Now, we're talking about items that are inserted, possibly deleted, and then other items inserted. So you count the total number of insertions. And if that were 1,000, then an array of size 1,000 would be sufficient. You don't have to worry about false overflow because it'll never happen. Now, it turns out this is the easiest solution, and there are many situations where this is what you're supposed to do because it's the simplest. Such as, for example, exploring a graph using breadth first search. Now, in an operating system, if your queue is supposed to run forever, say you have an operating system which has a queue and it runs continuously, then you can't use number 3 as a solution. Let's look at this, a linked list implementation of a queue. Now, this is an abstract diagram of the queues, where Z is in front, then M, R, and W is in the rear. So sometimes that's written like it's a tube, a double-ended tube where you push things in on one end and things pop out the other end. Now here, we need to have 2 pointers, a pointer to the front item and a pointer to the rear item, which means it's very easy to delete an item. All you have to do is do that. And now the new front, it's the same as deleting Z from the queue. Now, how do you add an item? Adding an item is not so, or inserting an item is not that difficult. What we have to do is create another node here, call this null, and put in the correct letter here, and change this null to be the pointer to the new item, which we can copy from here, and then change the pointer on the rear to point to that item. Now, this temporary variable will disappear when you leave the procedure. So, insertion is relatively easy. However, there is a problem. And the problem is, what happens when the queue becomes empty? What will happen to the pointers front and rear? Well, it turns out you have to write separate code for that situation. If you use the code for insertion or NQ and DQ that works when the queue is not empty, then when you go to use the same code, if the queue is empty, it won't work. You have to do separate things. And so that is a problem there, and I'll get to how we solve that. All right. This is a circular implementation of queue, circular linked list. We only need one pointer, but we have a dummy node here. The dummy node's item field is a don't care. It means that it's not that it's blank, it's that we don't care what it is because we do not plan to read it. So this picture represents a queue illustrated here abstractly, where things come in this way and out that way. Now, with this implementation, we don't have the problem of how to represent an empty queue. Here is, for example, what the picture looks like if the queue is empty. There's always a dummy node. If the queue has 3 items, there are 4 nodes. All right, now insertion into the queue is relatively simple. What we do is we change this pointer here to point to that one. This creates garbage in the sense that this one is no longer there. But you notice that the R has been deleted from the queue. All right, now insertion is more difficult. Let's imagine that we have this cube RTV and we want to insert the item H at the rear. Now, if you look at this carefully, you'll see that in order to point to this node, you would have to do a linear traversal with the entire cube. Now, you'd get a correct answer that way, but it takes O of n time to do that. And if you were doing that every time you did an insert, there are situations where things would be greatly slowed down. The queue might have 1,000 items in it, for example, or any number. So it turns out that you can insert an item into this queue in constant time by being somewhat tricky. All right, now, I've already done this in class, but I'll do it again. The way you insert an item is that you create, using the new function or something, you create a new node. So here is your new pointer, but we're going to call that temp because this variable is a local variable of the insertion routine, which will be deallocated at the end of the subprogram. Now, what we do here is we point up to here and we write the inserted item here inside that. So I guess we should no longer have an X because it's not a don't care anymore. We put that there. And then we proceed using this temp pointer to point this way here, and then we define the pointer for this temp variable to point to here, which is still the front item. There's a new rear item, but the front item hasn't changed. And this particular node becomes our dummy node. Now that means that this queue, which is a global variable, we're hoping, this is local, this will be deallocated. So what we have to do is redefine that pointer so it points to the new dummy node. And now observe. We now have the queue RTVH. Let's follow that along. We start here with the queue function. It points to it, the queue variable here, which is the global variable for the queue, points to the dummy node, which points to the front item R, next item T, next item V, and finally the rear item H, which of course points back to the front item, which points back to the dummy node. Oh, I made a mistake there. This one is the one that's eliminated here. This points to the dummy, and this link is eliminated there. So the rear item now points to the dummy, and the dummy points to the front item. An item which is either in a stack or a queue is there because it represents an unfulfilled obligation. Try to think of the theater line. Each person standing in line represents an obligation on the part of the seller, the theater, to sell that person a ticket. And similarly in a queue, if for example we're doing breadth first search, an item in the queue represents the unfulfilled obligation to visit the descendants or children of that item, of that node. Now, instead of just stack and queue, stack is last in, first out, queue is first in, first out. Those are examples of priority queues. The general idea of a priority queue is it holds items, and when you delete an item, you're required to delete the item which has priority. But the priority rule depends on how you set it up. If the structure is a stack, the most recently entered or last in has priority to be deleted. If it's a queue, the first in has priority. We can also have another kind of priority queue called a min heap, where whenever we delete an item, we delete the item that has minimum value. But that's still a priority queue. Now, of course, I can also have a max heap, where we delete the maximum item. And that's not a complete list of priority queues. For some application, we might have a queue where the priority for deletion is some complicated thing that would have to be figured out at the time. Now, in principle, a priority queue always has the same operators. We can make a new one, we can check to see if it's empty, we can insert an item, and we can delete an item, but we can insert any item, but when we delete an item, we're not allowed to choose which one. It's by priority.